We have detected gravitational waves. We did it.
Space is full of surprises, and just when we think we've figured it out, the universe throws us a curveball.
Two big, massive objects like black holes. You see that as the black holes spin around each other.
From planets where it rains metal to black holes colliding across time and space, recent discoveries have rewritten cosmic rulebooks. Ready to have your mind blown? Buckle up, because the universe is stranger than we ever imagined.
Chapter 1. Exoplanet Extravaganza. For centuries, humans wondered if there were other worlds beyond our solar system. The idea of planets orbiting distant stars was once pure speculation, but in the past few decades, exoplanet discoveries have exploded. Thanks to powerful telescopes and advanced detection methods, we now know that exoplanets, planets outside our solar system, are not just common, but incredibly diverse and often downright bizarre. The first confirmed exoplanet was discovered in 1992 around a pulsar, and since then, astronomers have identified over 5,500 exoplanets, with many more waiting to be confirmed. These planets come in all shapes and sizes. Some are Earth-like and potentially habitable, while others defy all logic. There are planets where it rains molten iron, gas giants hotter than some stars, and even rogue planets drifting alone in the darkness without a host star. One of the most exciting exoplanet discoveries is the class of super-Earths and mini-Neptunes. Super-Earths are rocky planets larger than Earth but smaller than Neptune, with some potentially having thick atmospheres and vast oceans. One of the most famous is K2-18b, an exoplanet in the habitable zone of its star that has shown signs of water vapor in its atmosphere. This raises the possibility that life, at least microbial life, could exist beyond Earth. Meanwhile, mini-Neptunes sit in a category between terrestrial and gas planets, with thick atmospheres and possibly liquid water beneath their clouds. Then there are the rule breakers, exoplanets that shouldn't exist based on what we know about planetary formation. WASP 76b is a hot Jupiter, so close to its star that temperatures soar beyond 2,400 degrees Celsius, 4,350 degrees Fahrenheit, causing molten iron to evaporate on one side and rain down as metal on the cooler side. HD 209458b, nicknamed Osiris, has a comet-like tail because its atmosphere is being blasted away by stellar radiation. And then there's TOI 3757b, a gas giant with the density of cotton candy, so puffy that scientists aren't sure how it stays together. Some of the most intriguing planets lie in the habitable zone, the region around a star where conditions might allow liquid water to exist. Proxima Centauri b, orbiting the closest star to our Sun, could have an atmosphere and even oceans. The TRAPPIST-1 system is home to 7 Earth-sized planets, 3 of which are in the habitable zone. These planets likely have rocky surfaces and could host life if conditions are right. And then there are rogue planets, giant worlds floating freely in space, untethered to any star. Some of these lonely wanderers, like Ogle 2016 BLG 1928, could be as small as Earth, yet they drift endlessly in the darkness. Their origins still a mystery. Chapter 2. Black Hole Revelations. Black holes have long been the most mysterious objects in the universe, but recent discoveries have made them even stranger. Once thought to be invisible cosmic sinkholes, black holes are now being observed and studied in unprecedented detail. From the first ever image of a black hole to bizarre mergers and new types of black holes, these cosmic giants continue to challenge our understanding of physics. In 2019, the Event Horizon Telescope, EHT, captured the first ever image of a black hole in the Messier 87 M87 galaxy. This historic image showed a glowing ring of superheated gas surrounding a dark core, the event horizon, beyond which nothing can escape. Then, in 2022, the EHT released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Unlike M87, this black hole is much smaller and more chaotic, with gas swirling at nearly the speed of light. Gravitational waves detected for the first time in 2015 have also given us a new way to observe black holes. When two black holes collide, they send out ripples in space-time that can be detected on Earth. Since the first detection, scientists have observed dozens of these signals, revealing a hidden population of black holes that were once impossible to detect. Some of these mergers have been particularly strange. One involved a 100 solar mass black hole merging with a much smaller one, an event so unusual that it raised questions about how black holes grow. Another mystery is the existence of impossible black holes. Some are so massive that they shouldn't exist, while others seem too small to have formed through traditional star collapse. Ton 618 is one of the largest known black holes, with a mass 66 billion times that of the Sun. Scientists still don't fully understand how these supermassive black holes formed so early in the universe's history. At the other end of the spectrum, astronomers have found a stellar mass black hole just 3 times the Sun's mass, pushing the limits of how small black holes can be. Even weirder, some black holes appear to be moving at high speeds, possibly after being kicked by gravitational waves. Others seem to be forming in dense star clusters, where they consume nearby stars, growing rapidly. One of the most intriguing theories suggests that primordial black holes that formed in the early universe, could still be lurking undetected. Some scientists even speculate that a tiny black hole could be hiding in the outer solar system, masquerading as the hypothetical Planet 9. While still unproven, upcoming space telescopes may finally confirm or debunk this wild idea. Black holes have also provided insight into the nature of time and space. In 2023, physicists studying extreme black hole environments suggested that time itself could behave differently near an event horizon, potentially offering clues about quantum gravity and the fabric of reality. Some even propose that black holes might not be just destructive endpoints, but could contain wormholes or even entire universes within them. Chapter 3. Gravitational Wave Discoveries. For centuries, the idea that space itself could ripple like water was purely theoretical. Then in 2015, astronomers detected gravitational waves for the first time, proving that these distortions in space-time, predicted by Einstein 100 years earlier, are real. Since then, the discoveries have only gotten more bizarre, revealing new insights about black holes, neutron stars, and even the fundamental nature of the universe. The first ever detected gravitational wave, GW150914, came from 2 black holes colliding over 1 billion years ago. The event sent ripples across the cosmos, finally reaching Earth and causing tiny distortions in space, so small they were a fraction of a proton's width. The fact that we could detect such minute signals is mind-blowing on its own, but the bigger revelation was that black holes regularly merge, something we had only theorized before. Since then, LIGO and Virgo, the 2 main gravitational wave observatories, have detected dozens of these cosmic collisions. Some mergers are relatively normal, involving black holes of expected sizes, but others have been completely unexpected. One of the strangest, GW190521, involved the merger of 2 black holes so massive that, according to previous theories, they shouldn't have existed. Scientists had to rethink how black holes grow. Perhaps they are merging in dense star clusters, creating massive black holes faster than we thought. But gravitational waves aren't just coming from black holes. In 2017, scientists detected GW170817, a signal from 2 neutron stars colliding. Unlike black holes, neutron stars don't completely disappear after merging, meaning this event also produced a massive explosion, known as a kilonova. Telescopes around the world caught the brilliant flash of light from the collision, confirming that these events are responsible for creating heavy elements like gold and platinum. In fact, the gold in your jewelry might have come from a neutron star merger billions of years ago. Gravitational wave detections have also revealed mystery objects. Compact objects that are too big to be neutron stars but too small to be black holes, existing in a so-called mass gap. One such object, detected in 2020, had a mass of 2.6 times the Sun, placing it right in this mysterious range. Could it be an entirely new type of star? Scientists still aren't sure. The latest surprise came in 2023 when astronomers detected the gravitational wave background, a faint hum of ripples coming from supermassive black holes merging across the universe. Unlike individual wave detections, this background signal is always present, suggesting that entire galaxies are warping space as their central black holes slowly spiral together. Some theorists even speculate that these waves could hold clues about exotic physics, perhaps even extra dimensions or remnants of the Big Bang itself. Chapter 4: Neutron Stars and Pulsar Mysteries. Neutron stars are the extreme leftovers of massive stars that have exploded in supernovae. They are some of the strangest objects in the universe, small but incredibly dense with mind-bending physics that scientists are still trying to understand. But even among these bizarre objects, there are special kinds of neutron stars like pulsars and magnetars that push the limits of what we thought was possible. A neutron star is born when a giant star runs out of fuel and collapses. If the dying star isn't massive enough to form a black hole, it instead compresses into a dense ball only about 10 to 15 miles wide, but with more mass than the Sun. To put that into perspective, a sugar cube-sized piece of neutron star material would weigh as much as Mount Everest. These objects are so dense that their gravity can bend light, making them appear larger than they really are. Among neutron stars, some rotate incredibly fast, emitting beams of radiation like cosmic lighthouses. These are pulsars, and they can spin hundreds of times per second. One of the fastest known, PSR J1748-2446 AD, rotates at a mind-blowing 716 times per second. If it was spinning any faster, it would break apart. Pulsars are so precise that scientists use them as cosmic clocks, and some of them even help detect gravitational waves. Neutron stars also collide, creating some of the most violent explosions in the universe. The 2017 detection of a kilonova, a neutron star merger, confirmed that these collisions forge elements like gold and platinum. But some neutron stars might take things even further. Scientists suspect that extremely massive ones may briefly form a quark star, an even denser object where neutrons break down into fundamental particles. If confirmed, quark stars would be a completely new type of matter, unlike anything seen on Earth. Even more extreme than pulsars are magnetars, neutron stars with the strongest known magnetic fields in the universe, 1 trillion times stronger than Earth's. If a magnetar were as close as the Moon, its magnetic field could erase all credit card data on Earth. These objects occasionally release enormous bursts of X-rays and gamma rays, sometimes detected across the galaxy. Some astronomers think magnetars might be responsible for some fast radio bursts, FRBs, mysterious, millisecond-long signals coming from deep space. One of the strangest discoveries about neutron stars is their ability to glitch. Even though they are incredibly dense and solid, some pulsars occasionally suddenly speed up for reasons scientists still don't fully understand. These glitches might be caused by the strange, superfluid interior of neutron stars, where quantum effects create behavior that defies intuition. Another puzzle is whether neutron stars could host exotic forms of life. While they themselves are incredibly hostile, some theorists suggest that planets orbiting neutron stars, if they had thick atmospheres, might be able to shield life from deadly radiation. These planets would be in a bizarre environment, with their sun being a rapidly spinning pulsar beaming deadly light across the sky. Neutron stars also challenge our understanding of relativity and quantum mechanics. Because their gravity is so intense, they create a perfect laboratory to test Einstein's theories. Some future experiments hope to use neutron stars to study gravitational waves, extra dimensions, and even the nature of dark matter. Chapter 5: Dark Matter and Energy. The universe is mostly made of things we can't see. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the universe. The rest? A mysterious combination of dark matter and dark energy, two forces that are invisible yet shape the very fabric of the cosmos. Scientists have been hunting for answers for decades, but the more they learn, the stranger things become. Dark matter is thought to make up about 27% of the universe, and although it doesn't emit, absorb, or reflect light, we know it's there because of its gravitational effects. Galaxies spin faster than they should based on their visible mass, and galaxy clusters remain bound together when, by all logic, they should fly apart. The only explanation? Some unseen form of mass is providing extra gravitational glue. The leading theory suggests that dark matter consists of some yet undiscovered particle, possibly weakly interacting massive particles, WIMPs or axions. But despite decades of experiments, deep underground, in space, and in particle accelerators, scientists have yet to detect a single dark matter particle directly. Then there's dark energy, an even bigger puzzle. While dark matter pulls things together with gravity, dark energy does the opposite. It pushes the universe apart. In the late 1990s, astronomers discovered that the expansion of the universe isn't slowing down as expected. It's accelerating. This shocking revelation meant that some unseen force, now called dark energy, was counteracting gravity on cosmic scales. Dark energy is estimated to make up 68% of the universe, yet we have no clue what it actually is. Some theories suggest it could be related to the vacuum energy of space itself, while others propose modifications to Einstein's general relativity. Recent observations have deepened the mystery. Measurements of the universe's expansion rate using different methods, one based on the cosmic microwave background, CMB, and another on nearby supernovae, have produced conflicting results. This Hubble tension suggests we might be missing something fundamental about the nature of dark energy or the very structure of the universe. Some physicists even speculate that dark energy could be a sign of a new force of nature, one that operates on cosmic scales. Another bizarre possibility, dark matter and dark energy might not be entirely separate. Some recent models propose that they could be linked through an unknown interaction, meaning the same mysterious substance shaping galaxies might also be responsible for the acceleration of the universe. And if that's the case, our entire understanding of physics might need an overhaul. Chapter 6: Cosmic Microwave Background and Early Universe. The universe as we see it today is vast, full of galaxies, stars, and planets. But rewind the clock back 13.8 billion years, and everything was crammed into a tiny, hot, and dense singularity. The Big Bang Theory explains how our universe expanded from that initial state, but how do we actually know this happened? The answer lies in the cosmic microwave background, a faint glow left over from the birth of the universe. First detected in 1964 by Arno Penzias and Robert Wilson, the CMB is often called the afterglow of the Big Bang. It's a nearly uniform background of microwave radiation that fills the entire sky, a remnant of the time when the universe was just 380,000 years old. Before that, the universe was too hot and dense for light to travel freely. Protons and electrons were locked in a chaotic plasma. But as the universe expanded and cooled, atoms formed, allowing light to escape for the first time. That light, stretched over billions of years by the expanding cosmos, is what we now detect as the CMB. At first glance, the CMB looks nearly uniform, but tiny variations in its temperature hold a wealth of information.
But these fluctuations are incredibly tiny. They're only at the level of 1 part in 100,000.
These fluctuations are the imprints of the universe's earliest structures, the seeds of galaxies and cosmic voids. The most detailed map of the CMB, created by the Planck satellite, has provided precise measurements of the universe's age, composition, and even its shape. According to these observations, the universe is 13.8 billion years old, consists mostly of dark matter and dark energy, and is flat on large scales. But the CMB isn't just a perfect confirmation of the Big Bang. It also poses some perplexing mysteries. One of the biggest is the cold spot, an unusually large, underdense region in the CMB that doesn't fit well with standard models.
And so people took it as an anomaly and started calling it a supervoid, something much bigger than we were used to seeing in the much smaller voids in the structure of the universe.
Some scientists suggest it might be the result of a massive supervoid, while others entertain wilder theories, like a collision with another universe in a higher dimensional space. Another puzzle is the horizon problem. The CMB is almost perfectly uniform, meaning all regions of the early universe must have been in thermal equilibrium. But how could that be if light didn't have time to travel between them? The leading explanation is cosmic inflation.
The way in which inflation explains the bang is in terms of a very surprising feature of physics, I think it's very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively.
A brief period of exponential expansion that happened within the first fraction of a second after the Big Bang. Inflation theory suggests that the universe expanded faster than the speed of light, smoothing out irregularities and explaining the uniformity of the CMB. While inflation is widely accepted, it remains an area of intense research as scientists try to figure out what caused it and whether it ever stopped completely. Recent studies have even hinted at unexpected asymmetries in the CMB, suggesting that the universe might not be as isotropic as we thought. Some physicists speculate this could be evidence of exotic physics, perhaps hints of a pre-Big Bang state or extra dimensions beyond our own. Future missions like NASA's CMB-S4 and the European Space Agency's Light-Bird satellite will provide even sharper maps of the CMB, potentially revealing new details about the earliest moments of the universe. By studying this faint cosmic signal, scientists hope to answer some of the biggest questions in cosmology, from what triggered inflation to whether our universe is just one of many in a vast cosmic multiverse. Chapter 7: Stellar Life Cycles. Stars may seem eternal, but they're actually living, evolving objects with distinct life cycles. From their chaotic births in massive clouds of gas and dust to their spectacular deaths, stars shape the universe in profound ways. Every element heavier than hydrogen and helium, oxygen, carbon, iron, even the gold in your jewelry, was forged inside a star. Without their life cycles, the universe as we know it wouldn't exist. Stars are born in vast regions of space known as stellar nurseries. These dense clouds of gas and dust, often lit by nearby stars, are breeding grounds for the new suns. Gravity slowly pulls gas together, forming protostars which heat up as they collapse. If a protostar gathers enough mass, nuclear fusion ignites in its core, marking its transition into a fully fledged star. The fusion of hydrogen into helium releases enormous energy, creating the light and heat that stars emit. The exact life path a star follows depends on its mass: small, medium, or massive. Low-mass stars, like red dwarfs, are the most common type in the universe. These tiny, dim stars burn fuel so efficiently that they can last trillions of years, far longer than the current age of the universe. Some of them will outlive the sun by orders of magnitude. When they do eventually run out of hydrogen, they cool and fade into white dwarfs, dense, Earth-sized remnants of their former selves. Medium-sized stars, like the Sun, live for billions of years before running out of hydrogen. When this happens, the star swells into a red giant, engulfing nearby planets. The Sun, for instance, will expand so much that it could swallow Mercury, Venus, and possibly Earth. In its final act, it will shed its outer layers into a glowing shell of gas called a planetary nebula, while the core shrinks into a white dwarf. The expelled material enriches space with elements that will one day form new stars and planets. Massive stars, on the other hand, live short, explosive lives. These giants burn through their fuel quickly, fusing heavier elements like carbon, oxygen, and even iron. But iron is a dead end. Once it forms in a star's core, no more energy can be extracted. The star collapses under its own gravity in a split second, triggering a supernova. These violent explosions briefly outshine entire galaxies, scattering heavy elements across space. Some of these elements will eventually end up in planets, or even in us. Supernovae leave behind either a neutron star or a black hole, depending on the original star's mass. Neutron stars are so dense that a sugar cube-sized piece would weigh billions of tons. If the star was massive enough, its core collapses completely, forming a black hole, a region of space-time so warped that not even light can escape. One of the most mind-blowing discoveries of recent years involves failed supernovae, stars that seem to skip the explosion and collapse directly into black holes.
The star that seemed to be there before very, very quickly and drastically dimmed in brightness in visible wavelengths that we see.
In 2017, astronomers watched as a massive star simply vanished without a trace. This suggests that some stars might quietly form black holes without producing a visible explosion, making them much harder to detect. Chapter 8: Galactic Dynamics and Mergers. Galaxies are the grand structures of the universe, vast collections of stars, gas, dust, and dark matter bound together by gravity. But they're not static. They move, collide, and merge in a cosmic dance that spans billions of years. Understanding how galaxies evolve helps us piece together the history of the universe and predict its future. Most galaxies fall into three main categories: spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way, have elegant rotating arms filled with young stars and gas. Elliptical galaxies, on the other hand, are more rounded and contain mostly older stars. Irregular galaxies are chaotic in shape, often the result of past interactions with other galaxies. One of the biggest mysteries in galactic dynamics is dark matter. Observations show that galaxies rotate much faster than expected, meaning there must be extra unseen mass holding them together. This invisible matter, which makes up most of a galaxy's mass, is only detectable through its gravitational effects. Without it, galaxies would fly apart. Galaxies don't exist in isolation. They interact, collide, and sometimes even devour each other. These encounters can trigger bursts of star formation, distort galactic structures, and even lead to the creation of new galaxies. The Milky Way itself has cannibalized several smaller galaxies in the past, their remnants still detectable in the form of stellar streams, long, thin trails of stars stripped from their original homes. The most famous galactic collision in progress is the Antennae galaxies, a pair of interacting spirals locked in a slow-motion crash. As they merge, gas clouds compress, triggering massive star formation. Eventually, they will combine into a single larger galaxy. But perhaps the most exciting galactic event on our cosmic horizon is the Milky Way Andromeda collision. In about 4.5 billion years, our galaxy will merge with its nearest large neighbor, the Andromeda Galaxy. Right now, Andromeda is hurtling toward us at 110 kilometers per second. When the collision happens, stars will be thrown into new orbits, some flung out into intergalactic space. The two galaxies will likely form a new, larger elliptical galaxy, nicknamed Milkomeda. While the thought of a collision sounds apocalyptic, individual stars are so far apart that direct impact between them are extremely rare. Our solar system will likely survive the merger, just in a completely transformed galaxy. One of the most dramatic galactic events ever observed was the starburst galaxy NGC6240, where two black holes at the center of colliding galaxies are spiraling toward each other. Eventually, these black holes will merge, sending out a powerful gravitational wave signal detectable across the universe. Mergers aren't just destructive, they're essential to galaxy evolution. Many of the largest galaxies we see today, including giant ellipticals, likely formed from multiple past mergers. Even our own Milky Way's spiral arms and central bulge were shaped by interactions with smaller galaxies. Beyond collisions, galaxies also evolve through interactions with their environment. In dense galaxy clusters, some galaxies are stripped of their gas by the cluster's hot intergalactic medium. This ram pressure stripping can shut down star formation, turning once active galaxies into dead gas-poor systems. The Virgo cluster contains several examples of such quenched galaxies that were once vibrant, but are now slowly fading away. Chapter 9: Solar System Surprises. Our solar system may seem familiar, but it's still full of surprises. Every new mission and observation reveals something unexpected, from bizarre planetary weather patterns to strange moons and unexplained cosmic oddities. Just when we think we have it all figured out, the universe throws us another curveball. One of the biggest shocks in recent years was the discovery of volcanic activity on Venus. For decades, scientists thought Venus was geologically dead. but new data from the Magellan and Venus Express missions suggest that at least one of its volcanoes, Idun Mons, might still be active. If confirmed, this would change everything we thought we knew about our closest planetary neighbor, showing that it is far from the lifeless, static world we once imagined. Mars has also continued to surprise us. The Perseverance rover has been hunting for signs of ancient life in the Jezero crater, where a long-gone river once fed a lake. But one of its biggest discoveries so far has been unexpected organic molecules, potential building blocks of life embedded in Martian rocks. While this doesn't confirm life ever existed on Mars, it does suggest that the conditions may have been right for it. Even stranger, new evidence from the InSight mission shows that Mars experiences Marsquakes, indicating that the planet is still geologically active beneath its surface. Further out in the solar system, Jupiter's moon Europa and Saturn's moon Enceladus are turning out to be some of the best places to search for extraterrestrial life. These icy moons hide vast subsurface oceans beneath their frozen crusts, and in Enceladus's case, jets of water have been spotted spraying into space, possibly carrying organic materials. The upcoming Europa Clipper mission will investigate whether Europa's hidden ocean could support microbial life. Even Pluto, once dismissed as a boring rock, turned out to be way more interesting when NASA's New Horizons spacecraft flew past it in 2015. The dwarf planet has mountains made of ice, a vast heart-shaped glacier, and a hazy blue atmosphere. Some scientists even suspect that Pluto might have a subsurface ocean, making it another potential candidate for astrobiology studies. Beyond Pluto, the Kuiper Belt and Oort cloud continue to reveal strange, icy objects that defy explanation. The most famous recent visitor was Oumuamua, a cigar-shaped interstellar object that zipped through our solar system in 2017. Unlike anything we've seen before, it accelerated in an odd way as it left our system, sparking theories ranging from exotic physics to, yes, possible alien technology. A second interstellar visitor, Comet Borisov, was spotted in 2019, further proving that space is full of wanderers from distant star systems. Another ongoing mystery is the hunt for Planet 9. Some astronomers believe that an undiscovered planet several times the mass of Earth lurks in the outer reaches of the solar system, based on the strange orbits of distant objects. Despite intense searches, it has yet to be found. Could it be a giant planet hiding in the darkness? Or, as some speculate, even a tiny black hole? Chapter 10. Next-Gen Missions and Technologies. Space exploration is entering a new golden age, with ambitious missions and groundbreaking technologies promising to reshape our understanding of the universe. From returning humans to the moon to the search for alien life, the next few decades could bring some of the most exciting discoveries in human history. One of the biggest upcoming milestones is NASA's Artemis program, which aims to put astronauts back on the moon by the mid-2020s. But this time, the goal isn't just a short visit. It's to establish a permanent lunar base as a stepping stone for future Mars missions. NASA, along with international partners, is planning a space station in lunar orbit called the Lunar Gateway, which will serve as a hub for deep space exploration. Private companies like SpaceX and Blue Origin are also developing technologies to support long-term moon missions. Speaking of Mars, the red planet remains a top priority. NASA's Perseverance rover is collecting rock samples that will eventually be brought back to Earth by the Mars Sample Return mission, which could offer the best chance yet to detect ancient Martian life. Meanwhile, Elon Musk's SpaceX is developing Starship, a fully reusable spacecraft designed to transport humans to Mars within the next decade. While ambitious, if successful, it could make interplanetary travel a reality. Closer to home, new telescopes are set to revolutionize our view of the cosmos. The James Webb Space Telescope, JWST, has already begun capturing breathtaking images and detailed data on distant exoplanets, galaxies, and even the earliest moments of the universe. But it's just the beginning. Upcoming observatories like NASA's Nancy Grace Roman Telescope and the extremely large telescope, ELT, in Chile, will push the boundaries of what we can see. The search for alien life is also intensifying. In addition to upcoming missions to Europa and Enceladus, The Breakthrough Listen initiative is scanning the skies for radio signals that could indicate extraterrestrial civilizations. The development of next-gen AI algorithms might help sift through the vast amount of data, improving our chances of detecting something truly out of this world. Another major leap forward is in propulsion technology. Traditional chemical rockets are slow and inefficient for deep space travel, but newer concepts like nuclear thermal propulsion could dramatically cut travel times to Mars and beyond. Even more futuristic ideas like light sails propelled by lasers or antimatter engines are being explored as potential long-term solutions for interstellar travel. Artificial intelligence is also becoming a key player in space exploration. AI-powered spacecraft and robotic explorers could autonomously analyze alien landscapes, react to unexpected challenges, and even build structures on the Moon or Mars before humans arrive. The Viper rover set to explore the Moon's south pole will use AI to search for water ice, an essential resource for future lunar colonies. Private spaceflight is booming as well. SpaceX, Blue Origin, and other companies are making space travel more accessible than ever. The idea of space tourism, once pure science fiction, is now a reality, with civilians already flying to the edge of space aboard Blue Origin's New Shepard and SpaceX's Crew Dragon. In the future, space hotels and even commercial moon bases could be within reach for those who can afford the ticket. One of the most ambitious upcoming projects is the James Webb successor, known as LUVOIR, a massive space telescope designed to search for life on exoplanets. If launched, it could directly image Earth-like planets in distant solar systems, analyzing their atmospheres for biosignatures like oxygen and methane. If we ever get confirmation of alien life, it might come from one of these next-gen observatories.